Salam and good day, Doctor. We are from Group 7, Section 4 for Subject Structure Design. My group member consists of Chin Yi Long, Ho Ji Jong, Tam Min Kai, Goh Zeng Zi, and me.
Good day, my name is Hu Zhijong, matrix number F200144. Today, I'll be presenting Introduction. In this project, a new block of school building is to be built in the school compound of MK Datuk Jaafar, located in Bukit Senyum, Johor Bahru. This particular school block is required to be a double-story building. The purpose of building this school block is to prepare for the increase in number of students for the upcoming semester as the school reopens. The school block is required to provide 12 classrooms, 6 each on each floor. The dimension of each classroom is designed to be 4.5 meter long and 6 meter wide. As for the corridor, the dimension is planned to be 31.5 wide and 1.5 meter long. Therefore, the total built-out area of the school block is set to be 236.25 meters square. Generally, there are two types of action that must be taken into account while designing the structural member of the building. The first one is permanent action. Permanent action does not vary in magnitude with time, and it consists of cell weight of the structure, weight of finishes, ceilings, and services. Second one, variable actions. Load will vary depending on the situation. It consists of the weight of people, furnitures, equipments, and other loads that can be removed. The material used for the construction of this building are concrete and steel bars. Concrete is well known for its high ability to withstand compressive strength. It is recorded that the compressive strength of concrete ranges from 15 megapascal to 30 megapascal. However, concrete is weak in tension. In order to solve this problem, reinforced steel bars are added into the concrete structural member, such as beams. The tensile strength of steel bars can range from 50 kN to 600 kN. Objectives. There are two objectives in this project. The first one, to conduct detailed design for beam components of the structure chosen. Second one, to design beam using actual practice according to proper standard of practice.
A very good day to Mr. Cole. My name is Jin Long, metric number AF200169. Today I'm going to present the continuous beam for beam AC3, first floor. For durability, fire and bond requirement, the structural class for our beam is X4 and exposure class according to table 4.1 Eurocode 2 is XC3. So, minimum cover regard to durability is 25 mm. For the minimum dimensions and axis distance for continuous beams made with reinforced and precessed concrete, since our fire resistance is R120 and B minimum is 200 mm, so the A is 45 mm. As mentioned in the previous slide, minimum concrete cover regard to fire is equal to 39 mm and the nominal cover is 49 mm. For loading and analysis, the characteristic permanent action for beam A to B3 is 31.73 kN per meter square and characteristic variable action is 11.96 kN per meter square. For beam B to C, the characteristic permanent action is 2.25 because there is no brick wall and slab on it, and the characteristic variable action is 0 because it is one-way slab. Design load is 1.35 GK plus 1.5 kK. For span AB3, it is 60.78 kN per meter, and for span BC3, it is 3.04 kN per meter. In this case, there are only two load case, which is all maximum load case and minimum maximum load case. For the elastic analysis, we found that the distribution factor for member AB is 0.37 and member BC is 0.63. For case 1 all span max load, the end moment is 172.05 kN per meter and the maximum shear force is 211.02 kN. We found that in case 1, the maximum bending moment is 194.39 kN per meter. For case 2 maximum minimum load, MAB is equal to 128.52 kN per meter and MBC is equal to 0.57 kN per meter. The end moment in this case is 121.36 kN per meter and the maximum shear force is 148.75 kN. So the maximum bending moment found is 136.97 kN per meter. That's all for my part and I will hand in to the next presenter.
Hi everyone, my name is Goh Zeng Zi, metric number AF200146. Today I would like to present the part that is continuous beam AC1, that is first floor. Now I want to explain the main reinforced part for span AB. Since the K value equal to 0.086 is lower than the K balance 0.167, thus the compression reinforced is not required. And the area of tension reinforced is calculated to 544 mm square and the minimum reinforced area equal to 147 mm square. And last is the maximum reinforced area equal to 4,800 mm square. From the value of area of tension reinforcement equal to 544 mm square, from this table, we can use 2H20 for span AB, and that is 628 mm square of cross-section area. For span BC, the K calculated value is equal to 0.1, is less than the K balance 0.167, so the compression reinforcement is not required. And the area of tension reinforcement they calculated equal to 696 mm square, and the minimum reinforced area equal to 147 mm square. The maximum reinforced area equal to 4,800 mm square, and the next slide will be show how many bar will be used from the calculated area of tension. From this table, we can use 3H20, that is 943 cross-section area, since we know that the area of tension reinforced is equal to 696 mm square. Next, I want to explain the part shear reinforcement. For the minimum length for spacing equal to 356 mm, and the maximum spacing equal to 0.75 multiplied by 525 equal to 394 mm. Since the spacing is less than the maximum spacing, thus we can use H6 300 mm for the whole span from A to C. That's all for me. Thank you.
The percentage of the tension reinforcement is equal to 0.0021. The reference reinforcement ratio P0 is equal to 0.005, and the percentage of required compression reinforcement P prime is equal to 0, because the compression reinforcement is not required in this case. Since the P is smaller than the P0, the following equation is used to calculate the L over D. The K is equal to 1.3 due to the beam is a continuous beam. The L over D allowable that we calculated is 107. The L over D actual is equal to 11.43. Since the L over D actual is smaller than the L over D allowable, therefore the deflection for the beam A to C/8 is acceptable. Just now we calculate the deflections for the span A to C. Now the step to calculate the deflection for the span B to C is almost the same as the span A to B. We can clearly see that the L over D allowable is much greater than the L over D actual. Therefore, the deflection for the beam span B to C is acceptable. Now we calculate the cracking for the beam A to C/8. The limiting crack width is equal to 0.3 mm, and the steel stress that we calculated is 322 Newton per millimeter square. By referring the table above, the steel stress that we choose is 360, and the maximum crack width is 0.3 mm. The maximum allowable spacing is equal to 50 mm. The bar spacing is calculated by using the equations: the width of the beam minus the 2 nominal cover minus 2 diameter of the link and minus the diameter of the bar, and divided by 2 when we provide 3 of the steel bar, and we get the spacing equal to 35 mm. Since the bar spacing is lower than the maximum allowable spacing, therefore the spacing is acceptable, then the cracking of the beam is also smaller. Now we can provide the detailing for the beam A to C/8. We can clearly see that the cross-sectional area for the B to C is the same, which the cross-sectional area is provided for the compression reinforcement. It is provided 2H20, which area is 622 mm square, while for the tension reinforcement is provided 3H20, which area is 943 mm square.
Hi everyone, I'm Tamin Kai, and today I'll continue to present the summary. In this summary, we'll try to focus on continuous beams only. The beams A to C/1, the beam size for the section AA and the section BB are the same, which is 200 times 600 millimeters. No compression reinforcement is required for the beam. However, the tension reinforcement for the section AA need 2 bars, while section BB need 3 bars. For the beam A to C/3, the beam size for the section AA is 200 times 600, while the section BB is 200 times 450. It needs 4 bars for the tension reinforcement and 2 bars for the compression reinforcement in both section AA and section BB. The beam A to C/5 is similar to the beam A to C/3. It needs 4 tension reinforcement bar and 2 bars for the compression reinforcement in both section AA and section BB. The beam size for the section AA and the section BB is the same as the beam A to C/3. For the beam A to C/7, the beam size for the section AA and the section BB are the same, that is 200 times 600. Both of them require 3 tension reinforcement bar and 2 compression reinforcement bar. Lastly is the beam A to C/8. The beam size is exactly the same with the beam A to C/7. And also the section AA and the section BB, it requires 2 compression reinforcement bar and 3 tension reinforcement bar. In a nutshell, a project construction will commonly include 3 stages, which are planning, design, and construct. The detailing design can be evaluated to ensure that the proposed dimension and the arrangement of the structural component are appropriate to the building. As an engineer, it is our responsible to ensure that the safety of the building and ensure the structure is strong enough to withstand any load that is exerted on it. This requires the precise calculation and every knowledge we have learned in this structural design subject. That's all from me. Thank you for lending us your ears. Thank you. Bye bye.